Hi everyone. In this video, I'll show you how to connect a Lumerical simulation to your PCell. So to get started, we'll start off at the very top here. Next to the same indentation as the default trace template, we'll add a new function. And I wanted to showcase this function called validate properties. So what validate property does is after a user inputs their parameters for a PCell, it'll check to make sure it makes sense. So on top of the initial check of the numbers type and what's allowed, you can add additional typing or conditions. So in this case, for my example, I'll use duty cycle. So if the duty cycle is larger than 1.0, which should not be the case because the duty cycle is a number between 0 and 1, and it represents the fraction or ratio of the amount of grading versus spacing. So here we can put a condition in that. If it's greater than 1, it doesn't make sense. So what we'll do is we'll raise an error, and the error to raise is i3.property validation error. And we'll pass in two things. First is self, and then second will be a string that says the current duty cycle is not valid. Only values between 0 and 1 are accepted. And this is pretty cool to play around with. I'll showcase it here. So we also want to return true otherwise. So how we're going to do that to play around with is let's set the default to 1.5, and then we'll try to run the script. And we should see an error here that tells us that we set the value incorrectly. So you can see here, we had an error, and then it tells us that there's an error validating the properties, and the cause of the error is our message. The current duty cycle is not valid. Only values between 0 and 1 are accepted. And this is a great best practice to do. It's really easy for designers to kind of narrow down what went wrong with their device instead of trying to dig through the code and possibly changing items that you didn't want to change. So with that, what we'll do next is we'll implement the Boolean we created earlier for the simulation geometry. Before that, though, I want to showcase what happens if we don't. So let's first attach this simulation this PCell to a simulation. So at the very bottom here, we'll go to the very end, and we will create a simulation object. And this object will be called i3. There's a function called device_sim, and inside that there's a Lumerical EME simulation. And it takes a few parameters. The parameters I have to give it first are, let's redeclare everything. So let's comment out everything, and we'll redeclare everything to make it easier to read. The first will be a simulation object for the brag grading. It'll just be a brag straight object. And then this time we'll make sure we pass in simulation geometry equals true. Just to utilize our Boolean. Next is the same as we did before. We'll create a layout called simulation layout from simbrag .layout. And then what we want to do is we can create the geometry to pass over to Lumerical, something called sim geometry. And this is a i3 device sim, and there is something called simulation geometry. And this takes some parameters. The parameter it takes is layout. So we pass in our layout object, and it'll convert it to the right format for us. And then finally, we'll have our simulation object with that Lumerical EME simulation. And what we want to do here is we want to provide the geometry object we just made. So sim geometry goes into geometry. And then there's also something called outputs. We can leave this blank for now. There's something called setup macros. These are macros you want to run at the very beginning when the file is loaded. They're akin to the setup scripts in Lumerical. It essentially calls the same thing. And then I think with that, we're good to try to run it. So at the very end here, what we want to do is we'll use our simulation object, and we'll tell it to inspect. So what this will do is line 100, where we declare simulation object, it'll create the whole simulation file, and then when we inspect it, it'll open it up, and we can do whatever we want with it. So we should be expecting Lumerical to launch twice with this kind of setup. We spelled setup macros incorrectly, so we spell it. set up macros. And this might take a bit longer. The reasoning is because we're passing quite the long device into Lumerical. And we'll showcase how we can avoid that in a little bit. So you can see Lumerical EME loads, and then in the background here, it's drawing all our geometries, and then it'll automatically draw the simulation region as we have defined based on the ports. So here's another thing we'll want to do in this video, where the region might not be enough for a simulation, so we'll put in our own custom parameters to set it. But as you can see, it did quite a good job automatically creating this simulation file. The port's on the right place, so we don't have to worry about placement if this was a one-to-one simulation. And everything else looks to be in place. You also notice that it drew cladding layers on top. This matches up with the PDK you're using. But you will have scenarios, for example, with this brag grading device where perhaps we want to draw more layers elsewhere. So looking at the EME object, we'll also notice that it's not set up correctly. So specifically, the periodic group is not set up correctly. We don't have the gradings defined where we can leverage this solver. So I want to go back and add that. So next what we'll do is we'll close this, and we'll kind of clean up our code so it draws a more efficient geometry first, and then we'll load in some parameters to set up the solver correctly. So first what we want to do is, instead of drawing that full length of geometry, why don't we just draw a short amount of it? Let's say 5 or so periods. And this keeps things small and simple. And then the goal is within this 5, we can have the most center ones be the unit cell. And this is a best practice I could do in Lumerical, where you draw a little bit additional on either side for gradings. In case today the source or the boundary conditions are not correct, this will confirm that they're correct because they're matching the actual device. So that's what we're going to try to create here. So we'll go back to our generate elements function under the layout. And then what we'll add immediately is, let's ask it if the self.simulation geometry is true. Then we'll only draw 5 periods. So we'll set the number of periods to 5. Otherwise, we'll just proceed as normal. And this will be useful for us to create the grading, and it'll automatically update the waveguide and the cladding and everything else. So it's very minimal code we have to add. The next thing that's more tricky to add is we need to locate our ports correctly and manually. So if you recall, the ports are exactly where the simulation ports will be located. So if we go with the regular one currently, they're located at the very beginning and end of our device. If it's 5, it'll locate it at the beginning grading and the end gradings. It won't locate it at our unit cell. So we'll have to tell it that, hey, you have to increment by, let's say, 2 periods to be in the right location. And then you have to increment by 3 periods to be at the correct end location. So what we'll do here is, under the trace template, there you go. We'll create our if statement. So if we're not doing the simulation geometry, then we'll do exactly what we did before. And we'll copy these ports. However, else, if we are doing the geometry, we'll put the geometry's ports in the right place. So instead of self.x, we should probably do we should probably just do self.period multiplied by 2, because the correct location is 2 periods past, since we want the 3rd period to be the unit cell. And then in the same way, the out port should be located at 3 periods away. So period times 3. And we'll set this y position to 0. And all that looks good. So what we'll do next is we'll give it a run, and we'll check in Lumerical to see if everything's working correctly. So you'll notice that we had a warning message in our console here. It's normal. It's just telling us that we put our port at a location that doesn't match the bounding box. So IPKISS will draw a bounding box around your whole geometry. And if your port's located weirdly, it just gives you a warning in case it was unintentional. So here you can see this is our new geometry simulation object. It's a lot more refined. The ports are located where we want them to be. The boundaries are located where we want them to be. And what we want to do next is we want to set up the EME solver to probably do this and allow us to simulate a periodic grading. So a few values here that we want to change are the background material. We're going to change it to the same background material as the cladding. It's just a fail-safe. Because of situations, for example, like this, where on the Z boundary, we are kind of free space and the cladding. So if it detects the raw material, we could get some non-physical numbers. And then what we also want to do is we want to divide this unit cell into two sections. So right now the span is 0.32. We want to make it 0.16, and there's two spans. And then that'll divide the cells into two sections. That way we can tell it to create a periodicity starting from cell 1 to cell 2. And then we can stamp that as many times as we want using the period function here. So we'll do that right now. We'll close the EME simulation and we'll return to the code. So what we want to do is at the very end, under these setup macros, we can give it some additional instructions. So the first thing we want to do is we want to go into setup macros and create something called i3 device sim.lumerical macros. So it's lowercase lumerical macros .eme setup. And this is a built-in function that IPKISS has specifically for EMEs. And we can use it to create the group spans we mentioned earlier. So the group span should be equal to the brag objects period divided by 2. And it should end at the next period divided by 2. So what this will do is it'll make that 0.32 we saw earlier into half of the value, and it'll split our unit cell in half. Next, what we want to give it is the number of cells, and this refers to the number of cells we have. So we have 1 cell each, and that's the second column of that EME solver object. And with that, we're done our first command. The second command is a little more tricky, so we have to move outside of what is predefined by IPKISS, and luckily they provide a more generic function called macro that lets us do that. So in macros, we can issue something called commands, which is a list object. And in commands, we can provide a list of strings that function just like the LSF script. In fact, they'll be read directly by Lumerical as such. So what we can do is we'll select the EME solver, and then we will set its energy. I'll just copy over everything from my finished file. So we'll set its energy conservation to conserve energy. We'll create a Y span, and the Y span is a F string. This lets us use variables, so we can put in our simulation brags waveguide width and set the corresponding units to it. And this lets us control how far or how close that Y span of the simulation boundary is. Next, we'll create our background material object, and we'll set it to silicon oxide. And then we'll create the periodicity group for the last 3 lines. So the start cell group will be the first cell, the end cell will be the second cell, and then we'll repeat it 500 periods for our simulation. And then what we'll want to do next is in the outputs, kind of building up for later videos, we'll want to export a S matrix. So we'll do a i3.deviceSim again, and then this time will be a Lumerical an S matrix output, and then it takes in 2 variables. First is the name, we'll call it S matrix, and then the wavelength range, and we'll set this to 1.5, 1.6, and 100, and this will be in microns. So that's 1.5 microns to 1.6 microns, and there's 100 points in between. And with that, this should be good to go. So we'll run it again and check if the simulation is set up correctly. So I also want to mention here with this command value, you could also load in a LSF script that you had before. So it makes converting from pure Lumerical to this a lot easier. So I think we called the wrong function somewhere. Let me take a look. So our hint is length 10 microns. Never encountered this error before. Set of macros. No, they look correct. Huh. Very odd. Oh, yeah. For some reason, my PyCharm keeps adding these additional lines at the top. I'm sure I'm clicking something accidentally, but we'll just delete that line at the very top, and everything should work. So we got our warning. That's good. And then our simulation is launching. And then our simulation draws as expected. Seems like the ports are set up correctly now. We have a new error. Oh, select EME. Yes, I had a typo here. EME should have a quotation here. I should use double quotes. So if you're in Python and then you have quotations where you need to add quotations within the string, you can use alternating quotes. So I start with a single quote, and then inside I use a double quote. So hopefully with that, all the issues are resolved. So that looks good. I think it did an extra amount at the end that I was expecting. In here, launched it for us to inspect. So everything looks correct now. You can see our Y span is shorter. It looks like the unit cells are properly defined by these 3 lines. We have one cell here and another cell over there. We can open the object. The background material is set correctly, and we have a period group correctly set up. So what we can also do now is we can run the device, and we can check if the results make sense. So if everything goes well, we should be seeing a filter response. So here I'll set a wavelength sweep, 100 wavelength points, and we'll visualize the results. They look good. So we'll showcase our S21. So the transmission is demonstrating a filter response, and then the reflection response should be in, I believe, 1.1. There we go. So our reflection response. So our device is working correctly. So everything's quite good. And that'll bring us to the end of this video. And in the next video, we'll showcase how to create a simulation for more complex devices that are going to be built upon this basic PCell. Thanks for watching.